Hello everyone, and welcome to Chapter 5, the chemical quantities and reactions. And in section 5.7, what we're going to do today is we're going to look at the mass calculations when we put them into the chemical reactions. So now not just the molar relationships, but the actual grams, like how many would you physically have if you actually did this experiment or this reaction was actually occurring. And so in order to do mass calculations in equations, first thing we'll have to do, of course, is use the molar mass to convert grams to the moles. If it's not given in moles, you'll have to write that mole factor from the coefficients in the equation, convert moles to what you have to moles to what you want or desire, and then convert those moles that you get at the end into grams of that substance. So our first example here, suppose you want to determine the mass of ammonia that can be produced from 32 grams of nitrogen. And so we look at the balanced equation and we notice that you have 1 nitrogen mole, 3 moles of hydrogen, and to produce 2 moles of ammonia. So we know that if we look it up, 1 mole of nitrogen's 14, so 14 times 2 is 28 grams of nitrogen. We know that 1 mole of N2, notice we have to do the whole molecule in this case, is 28 grams of nitrogen, and so we can use that to convert the 32 grams of nitrogen by its molar mass ratio of 1 mole of nitrogen to 28 grams, which allows us to cancel grams of nitrogen, and that leaves us with 1.1 mole of nitrogen. So that's step 1. We find how many moles of what we're given, what we have. The second step is we have to write the molar ratio, or the mole factor as they call it in this book, so that we know that 1 mole of nitrogen is going to react with 2 moles of ammonia, and so we can write this either way, with nitrogen on top and ammonia on bottom, or ammonia on top and nitrogen on bottom. And so that gives us our coefficient. So we can then do what we have, which is the nitrogen, and we can use the molar ratio, or mole to mole factor, because we know that 2 moles of ammonia will react with 1 mole of nitrogen, so that will give us 2.2 moles when we get rid of these moles of nitrogen. So the last step, now that we have moles of ammonia, we can say we need to know how much 1 mole of ammonia is. 1 mole of ammonia is 17 grams. That's 14 plus 3. I'm getting that from the periodic table, remember? And so our conversion factor is 1 mole of ammonia over 17 grams, or flip it, either way. And so we can set that up to have 2.2 moles of ammonia times 17 grams of ammonia over 1 mole. And of course we have to put moles on the bottom here so they cancel. And that is going to give us grams of ammonia. So what that told us was how many, we started with a certain amount of nitrogen, and by knowing that we had that, we could convert that to grams of ammonia. Okay, and so that's exactly what we did. So let's look at some learning checks with this and work this out. Okay, how many grams of oxygen are needed to produce 45.8 grams of Fe2O3 in the following reaction? And it's already balanced for you. And so what I want to do is I'm going to work this through with those 4 steps, but I'm going to do it all in one step. And this is how I work these, and I do it because I can use this where I just cancel units out. And so what I want to do, alright, is first I know that what I have is 45.8 grams of Fe2O3, so I know I'm going to start with that. 45.8 grams of Fe2O3, okay, and then I'm going to draw a line across here. Alright, and so the first thing I'm going to do is what? I'm going to convert this to moles, and I know I've got grams of Fe2O3 up there, so I'm going to have grams of Fe2O3 down here because I know I want them to cancel. And so I'm going to have to go to moles first. So how many grams is 1 mole of Fe2O3? And if you look up the iron, 2 irons, and 3 oxygens, I think you will find that it's 159.7. That's what I found when I did it. So 159.7 grams of Fe2O3 is what 1 mole of Fe2O3 will have a mass of. Okay, now once I've done that, I go ahead and check. Oh, I get to cancel something out. I get to check that off. All right, so now I'm left with moles of Fe2O3. What am I trying to find? What is desired? The O2. All right, so I know if I'm using my factor label or my cancellation, or some people call this dimensional analysis, I'm going to have moles of Fe2O3 down here because I'm going to cancel that next thing. So I know that for every 2 moles of Fe2O3, I'm going to have how many moles of oxygen? 3. Okay, so I'm going to put 3 moles of oxygen up here. See how I do that? Because I know that that is, in theory, according to the equation, how those two things will react. All right, and that allows me to do what? Cancel moles of Fe2O3. Now I'm left with moles of oxygen. What am I wanting to do, though? How many grams of oxygen? And so I know if I'm going to do dimensional analysis, the next thing is going to be moles of O2 down here. So I can cancel that. How do I go from moles of oxygen to grams of oxygen? Well, I know that 1 mole of oxygen is equal to what? 32 grams. Now make sure when you're doing this, you looked up oxygen, it's 16. But remember, this is oxygen, the molecule. So I have 2 of those, and so that makes that 32 grams. I get to cancel. All right, and then that is going to leave me with these units, and that's the units I want. So I know I've done everything correctly in my dimensional analysis. And so now all I have to do is I multiply everything on the top. So you're going to do 45.8 times 3 times 32, and then you're going to divide it by 159.7 and hit enter, and then divide it by 2 and hit enter. And if we did that correctly, we should get 13.8 grams. So that would be B. All right, so when they're doing it the long way, what they did, like we did, they found out what the molar mass or molecular mass of Fe2O3 was. And they came up with their conversion. They converted the 45.8 grams that we were given of Fe2O3 to moles. Then they took those moles that they calculated, and they are going to multiply it by the molar ratio according to the chemical equation. So those moles times the 3/2 ratio to get moles of oxygen, and then moles of oxygen times the molar mass ratio gives you grams of oxygen. So what they're doing in 4 steps, all I'm doing is I'm combining it, and I am using the analysis that I told you so that I can cancel each one of these out as I go along and get that. And so you can do it in steps like this, or you can do it in one long step. Okay, so let's try another one. Make sure that you pause and try to work this so we can see if you can do it, and then when you're done, come back. Okay, the reaction between hydrogen gas and oxygen gas will produce 13.1 grams of water. And the question is, how many grams of oxygen reacted? And I just want to say here, if everything worked according to the equation, then you would have 2 moles of hydrogen gas and 1 mole of oxygen gas exactly, and you would produce 2 moles of H2O, water. Okay, but most of the time you don't have the exact amount that you have in a balanced equation. You have a different amount, and so in this case we have 13.1 grams of water that's produced. And so what we're going to do is we're going to back calculate and try to see if we can figure out how much oxygen we used to produce that. And so my method would be what? We start with what we have, what we're given, 13.1 grams of water. Not a very straight line. All right, what's my first step? I know grams of water will go down here. So my first step is what? Convert it to moles. That's right. So 1 mole of water is going to be 18 grams of water. Same thing. So then I can cancel. And then what am I trying to find? I'm trying to find grams of oxygen. And how do I get from grams of water to grams of oxygen? Well, I'm going to have to get from moles to moles. And I know that moles of water will have to be on the bottom so that it can cancel out the moles that were on top in the previous one. And so 2 moles of water will react with 1 mole of oxygen according to my equation up there, which allows me to cancel moles of water. And then in order to get to grams of oxygen, I need to know how many grams there are in 1 mole of oxygen. And remember, it's a molecule, so that's going to be 32 grams of oxygen. And so that will cancel moles. And I know I'm right because my units are correct. And so 13.1 times 32 divided by 18 equals, and then divided by 2 equals. Why do I do that? Got any idea? I'll write down what I got. The reason I do this and enter in between each time is because sometimes if you don't, your calculator will not be your friend, and it will do something that you didn't necessarily want it to do. So I always try to make sure that I don't give it an opportunity. So that's why I multiply everything on the top, and then I divide by what's on the bottom, and then hit enter or equal, and then I divide the next thing on the bottom and hit enter or equal, and so that I get this. And that way I make sure that I don't make some silly calculator mistake. Alright, let's see how we did. Converted to moles using the 18 grams. Then the molar ratio, 2 moles of water to 1 mole of oxygen to give us moles of oxygen. Then we said 32 grams of oxygen is 1 mole, and so then that gave us grams of oxygen. So again, if you want to do it stepwise or you want to do it all in one long thing like I do, either way, that's fine. Now, I do want to bring one thing up about this. In the nursing, and this is mainly for like the nursing, I've seen this a lot in the nursing profession. What they like to do is something called desired over have times quantity, and you may see that or you may have seen it if you've got any training. And so what I want to show you is I want to show you how these are similar and how you can do it this way. Now, if you're going to do this desired or ordered over have times quantity, this is only good for going from mass to mass. Okay, so like if you have so many grams of one thing and you want to know how many grams of the other. Okay, all right. So our problem is going to be that magnesium hydroxide reacts with hydrochloric acid in the stomach to form magnesium chloride and water. And this is the reaction that it's going to use. This one's not balanced yet, but I'll show you. I'm going to balance it for you. If you have 40 grams of stomach acid, how much magnesium hydroxide would it take to neutralize all of it? Okay, and this is a neutralization equation, so this is what we're doing here. Now, if you want to do this, all the steps, what you'll do is the first thing you'll do is you'll balance this equation. All right, then you'll find the molar masses of all of these players, and then we will do the calculation. Okay, so if you want to put me on pause right now, I know you don't have this particular problem. I added this, so if you want to stop and write it down and everything, go ahead and try to work it, and then we'll go through the steps. Okay, so as I said, the first thing you're going to do is balance the equation. And you remember how to do that. You have to get the molar masses, and you're going to have to get that anyway, right? So you're gonna balance the equation with numbers of elements. All right, so you've got one magnesium here, one magnesium there. You've got an H2 and one H here. You've got a chlorine, you got two chlorines there. So you aren't balanced, all right? And it's always check and see if you're balanced or not. And so if you go through that balancing process, this is what you should come up with. So this is our balanced equation. So basically remember that this means 1 mag hydroxide plus 2 hydrochloric acids gives us 1 mag chloride and 2 waters. All right? And so the next step would be to find the molar masses. And you know, you're going to add these up. So I've given you from the periodic table, so you don't have to look out anywhere else, the magnesium, the oxygen, the hydrogen, and the chlorine. So you should be able now to put me on pause and figure up the molar masses of all of these molecules. Now, once you've done that, we've balanced and we've done the molar masses. Now, if I was doing this the way I've been showing you with the dimensional analysis, okay, basically once we balanced our equation, then we could use our molar ratios to work this problem. We do not have to worry about the molar masses. If you're going to do it with the molar mass ratio, you do a little more of your work up front, and then it's less work at the end. Okay, so I'm going to show you how to do it both ways. So the molar ratio way would be, we have 40 grams of HCl. All right, and so we're going to multiply it by everything we need to. Okay, so just do it like this. All right, so I'm going to do 40 grams of hydrochloric acid, so this will be grams of hydrochloric acid. All right, and so how many grams of hydrochloric acid are in 1 mole of hydrochloric acid? Well, this is the total amount of 2 of these. So if I was doing this method, I probably would not have even done this. So what I'd do is I'd add just 1 mole of HCl up, because that's what I'm looking at, 1 mole. Or I guess you could say 2 moles is equal to 73 grams, but I usually just do the mass of 1 mole. So 1 mole is actually 36.5 grams. 35.5 for the chloride and 1 for the hydrochloric acid. Like I said, you could either do this or you could say 2 moles over 73 if you're going to try it both ways, which, whatever. Alright, so that gives us grams and grams. Alright, so now we're to moles. We do the molar ratio. We know moles of hydrochloric will go on the bottom because we're going to cancel these out. So for every 2 moles of hydrochloric acid, we're going to have 1 mole of mag hydroxide. Okay, and then I know moles of mag hydroxide. It's going to go on the bottom. And so 1 mole of mag hydroxide is how many grams? 58.3 grams, if I haven't made a mistake on that. And that's going to give me grams of mag hydroxide, right? Now, at 40 times 58.3 divided by 36.5 and then divided by 2, and that should give me, if my calculations are correct, 31.9 grams. Okay, so that's doing it the traditional way. I did not have to do this step in order to do this. I just used my molar ratio. So I used the 40 grams I was given, then I used the molar mass of hydrochloric acid, the molar ratio between hydrochloric acid and mag hydroxide, and then the molar mass of the mag hydroxide, and that gave me my answer. Now, the molar mass method, or this desired over half times quantity, I have figured out the two things I was looking at was this and this. I do have to balance the equation so I see how many grams there are, so I do have to do that step, and then I do this step. Alright, and so now all I have to do is I say, okay, what do I have? I have hydrochloric acid. So I'm going to go ahead and multiply my quantity first. My quantity is 40 grams, okay, times what I have, which is the acid. Times what I want, desired, which is mag hydroxide, and that is 58.3, divided by what I have, which is 73 grams of HCl. And this was HCl, so really they still cancel. Alright, and then that, if you multiply that out, you're going to also get 31.9 grams. So what this is again is quantity times desired over have. Okay, and if you get to nursing school, you're going to see that. That's how you do these dosage calculations a lot of times and figure out how many pills you're going to give somebody to give them the right number of milligrams or whatever. Okay, so that is going to give you the correct answer as well. So it's kind of, you do all the steps and then just plug in, or you can just do this step and then you still would find these two items, but either way. So whichever way you want to do that final step, it's up to you. I just wanted to make sure that you'd seen this, because you will see that again probably in dosage calculations and pharmacology maybe and things like that. Okay, and that wraps it up for section 5.7. And the last section, which is 5.8, is going to be energy and chemical equations.